You know, it's one of those things we see every day but maybe don't really think about. There's this invisible force at work all around us, in the oceans and lakes, even in the glass of water sitting on your table. It's the force that decides if something sinks or floats. Today, we're going to pull back the curtain on the science of buoyancy.
And this is the central puzzle, right? It just seems to defy all logic. You toss a small pebble into a pond and punk, straight to the bottom. But then you see a gigantic ship made of literally thousands of tons of steel just floating there. How on earth is that possible? Stick around because by the end of this, you'll know exactly how.
So, to get to the bottom of this mystery, we've got to start with the basics. We need to understand the environment that these objects are in. It's not just water, it's a whole category of stuff. Let's start right there.
The whole secret really boils down to this one word: fluids. Now, a fluid is just any substance that can flow. So that means all liquids, like water, but also all gases, like the air that's all around us. And the really crucial thing about fluids is that they exert pressure in every direction, sideways, down, and, this is the important one for us, upwards. That upward push is where our story really begins.
I'm sure you've felt this yourself. You try to push something like a cork or a beach ball under the water, and you can feel the water fighting you, can't you? It's pushing back up against your hand. The second you let go, whoosh, it just shoots right back up to the surface. That resistance, that push you feel, that's a real physical force.
Or think about this. You try to lift a big rock from the bottom of a creek. While it's still underwater, it feels manageable. But the moment you lift it out of the water and into the air, suddenly you feel its real weight. It feels so much heavier. That tells you something in the water was helping you out, giving it a little lift.
And that upward push, that helping force we've been talking about, well, it has a name. It's called buoyancy. Sometimes you'll hear it called upthrust. It's simply the upward force that any fluid, liquid or gas, exerts on an object that's placed inside it. This one single force is why we can swim, and it's why those massive ships can float.
Okay, so we've put a name to the force, but the really big question is, where does it come from? I mean, why does water push things up? The answer is hidden in a fundamental property of all fluids: pressure. And this, right here, is the big aha moment. Now, take a look at this diagram. It seems really simple, just a mug submerged in water, but it holds the entire secret. See those arrows? They show the pressure that the water is pushing with from every single direction. Now, the forces on the sides, they just cancel each other out. The real action is what's happening on the top versus the bottom.
Now, this next part is the most important rule for understanding everything that follows. It's simple. The deeper you go in a fluid, the greater the pressure gets. Just think about a submarine diving deep into the ocean. The incredible pressure it has to withstand comes from the weight of all that water above it. This simple fact is the true cause of buoyancy.
So, let's go back to our mug. Look at the top surface, which we've labeled A. It's at a certain depth, right? So the water above it is pushing down on it with some amount of force. But because it's not very deep, that pressure isn't super strong.
But now, look at the bottom of the mug, at surface B. Because B is deeper in the water than A is, the pressure down there is greater. This means the force from the water pushing up on the bottom of the mug is stronger than the force pushing down on the top.
And there you have it. You've got a weaker downward push on the top and a stronger upward push on the bottom. The difference between those two forces results in an overall, or net, upward force. And that net upward force is exactly what we call the buoyant force. It's literally born from this pressure difference. Okay, so we know that buoyancy is an upward force caused by this increase in pressure with depth.
But is that force always the same? Is it a constant? Nope, not at all. Let's dig into the two key things that determine just how strong that buoyant force really is.
So the first factor is the volume of the object, how much space it takes up in the fluid. Now this one is a little counterintuitive. It's not about how heavy the object is, it's about its size. So if you take two balls that are the exact same size, but one is made of really heavy iron and the other is made of lighter aluminum, they will both experience the exact same buoyant force when you submerge them. The more volume you submerge, the more upward push you get.
The second factor is the density of the fluid itself. A denser fluid, like salt water, has more stuff packed into the same amount of space. That means it exerts more pressure at any given depth, which creates a stronger buoyant force. You've probably felt this. It's why it's so much easier to float in the salty ocean than it is in a freshwater lake or a swimming pool. The ocean is literally pushing you up with more force.
All right, so this all sounds good in theory, right? Pressure, volume, density. But can we actually see this force at work? Can we measure it? Absolutely. Let's walk through a very simple experiment that makes this invisible force totally visible. So, first things first, we'll take a metal cylinder and hang it from a spring balance. This will tell us its true weight, just hanging in the air with no other forces acting on it. And there we go. The scale reads 150 grams. That's our baseline, the cylinder's real weight. Remember that number. Okay, now watch what happens as we start to lower the cylinder into a beaker of water. The instant it touches the water, that buoyant force starts to push up, and you can see the reading on the scale begin to drop. And look at that, it now reads 140 grams. The cylinder didn't actually lose 10 grams of weight, of course. This new reading is called its apparent weight. It seems lighter because the water is already helping to hold it up. And finally, we'll submerge the cylinder completely. Now it's pushing aside the maximum amount of water it can, which means it's getting the maximum possible buoyant force from the water. And the final reading is 120 grams. So it started at 150, and now it appears to weigh 120. That 30-gram difference, that's the buoyant force. We've just measured it. The water is providing an upward push that's equivalent to the weight of 30 grams. So, as we just proved, the buoyant force makes an object seem lighter than it really is. And this brings us right back to our giant steel ship. If you just had a solid block of steel, it would sink. But a ship is shaped like a huge bowl. It's mostly empty space inside. That shape displaces an enormous volume of water, which creates an equally enormous buoyant force pushing up. And that upward force is strong enough to perfectly balance the ship's incredible weight, allowing it to float. So, we've cracked the code. Buoyancy is this amazing upward force that allows even the heaviest things to float. But that leaves us with one last, really fascinating question to think about. If this upward force is always pushing things up, how in the world does a submarine manage to dive?